Okay, so let's get started. And this is the second lecture of sparse optimization. And at the moment, I hope everybody has already registered for piazza.com. You get an account for piazza.com. If you don't have one, and if you don't have a USTC email, you can send an email to either me or one of the TAs, and we're going to add you to the website. Okay, and we're going to conduct a lot of important activities on this website, such as homework solutions, homework discussions, online seminar, all kinds of things on this website. So I'd say, at the end of this class, you're going to see that more than half of the materials actually you can find on this website. So make sure you have an account. Okay, there are several things I would like to mention at the beginning of this lecture. If you look at this website, you're going to see that we have updated lots of notes. First, we have this FAQ. FAQ stands for frequently asked questions. Basically, it's a question and answer, and it's supposed to answer lots of the common questions. So I won't repeat those because you should be able to see it from your laptop, from your iPad. Alright, so if you send me questions, feel free if you have general questions about this class, what will be covered, what will not be covered, or your comments, your suggestions. Everything you can send to me via this website, and if I see this question is related to the general audience, I'll put it in the FAQ. Alright, so and we also already have a student asking questions. And I think this is a great question. I pretty much get the question like 30 minutes after this question was posted. Basically, this question was asking about, say, what will be the KKT condition if the objective function is not differentiable? Right. So this is a great question. So, and we already got the students answering this question. I think this is a great answer. And we also have TA answering similar questions and also follow-up discussions. Right, so take a look, and this is a great example. It's a great question and a great example. All right, so this is number 2. Number 3, we have posted a homework. There will be one set of homework questions every week. So this homework is actually for the first 3 lectures. So this homework, if you open it up, it has like 6 different questions. You should be able to download the questions. If you find any exercises difficult, by the way, there will be like 1 or 2 exercises very difficult. You're gonna see. Feel free to ask questions here, discuss here. Homework is for collaboration. All right. Okay. Now, some of you will. Now I'm gonna ask some of you to scribe this lecture. And you also need to practice LaTeX for participating online discussions. All right. So we posted a set of notation. Right. So the notation list has been added to the class homepage under resources. What it basically does is tell you, just to formalize the notation. You go to. You click on class. Yeah, you can click on class. It goes down somewhere. Is there class? Yeah, resources. So click on course page and click on resources. All right. Then scroll down. You're gonna see a bunch of resources. All right. There's let me tell you roughly what these are. Right. There are 2 text files. Right. So one text file is called macros. This defines a bunch of standard macros you're gonna use. And this notation list.tex is the source file for this PDF file. Right. And this PDF file, if you opened it up, it's going to tell you what you should do in terms of notation. Right. So it's like a standard list of notation. What we're going to use. So what we're going to use for the real. Set of variables for complex space, for integers, and for other stuff. If you miss some notation, it's okay. If you use it wrong, I'm not going to kill you, but try to follow these notations, so others can appreciate. All right. Okay. Now, some of you are gonna scribe the lecture. So this is what I'm gonna do. I'm gonna send you the LaTeX source files of the PDF. So for example, this is the second lecture. I'm gonna send you the PDF files, all the source files. So you're gonna scribe. If you are asked to scribe a lecture, it means you're gonna listen very carefully to what I say, right? And also the questions from the students, right? And then write down almost everything. Now compare to the lectures and put the extra stuff into the lectures. Right? This is what you're going to do. All right. And now I'm going to only ask 2 of you to do every lecture, every maybe 2 hours. Right? So you only need to do 2 hours, and you're going to benefit from like the collective 30-hour effort. All right. Okay. Now when you add stuff to this LaTeX file, to this LaTeX, I should try to follow the notation. All right. Okay, and again, homework 1 is over there already. So let me go back to the question and answer sheet. Okay. So there's another one called KL inequality and global convergence. This is not so much related to this course specifically, but this is something I'm reading. So I read about this. I read about something called a KL inequality, and then and wrote the note here. And feel free to read it if you find it interesting. It's related to local convergence, subsequence convergence versus global convergence. If you know what that means. Okay. Now this lecture we're actually going to start from this online collaboration. We're going to start talking about interesting smart optimization models and applications first, right? Kind of motivate the rest of this course. So for every model and application, what we're going to find out is the background. So what has motivated people to develop such model and application, and then basically tell you what is sparse. Okay, and then let's give you the models. Give the optimization model, and then what you're going to get out of this model. It's called benefits of solving this model, and any references if you want to read further. Okay, so there are a bunch of postdocs here already, and maybe some of you have read those. So I'm going to go through these quickly. The first and the most basic compressive sensing, or like something called sparse optimization model, is compressive imaging. Actually, this is what has motivated lots of researchers to do sparse optimization. Here the background is a natural image, like what you see in your naked eye. It's got natural image. A natural image as an array of pixels. Do you want to see it larger? It's too small, huh? Right. So is it better? But all right, something like this. Okay. So we're gonna stay here. So basically, a natural image. A natural image is just a bunch of pixels, a bunch of points, right? The background is people find it highly compressible. That's why you can use a high resolution camera, take an image, and at the end of the day, it becomes like 20 kilobytes. So you can send the image to your friends via email. But the fact that natural images are highly compressible makes it possible to sense this image, means acquiring this image, not pixel by pixel. And if you do it pixel by pixel, it is called a raster scan, point by point raster scan. Instead of doing a pixel by pixel scan, you can try to sense this whole image, just add a small number of linear combinations of these pixels. All right. There are actually hardware devices to do this, and the types of these hardware devices are not small. They're like the 5 different types. I know 5 different types hardware devices to do such sensing not pixel by pixel, but sense a small number of linear combinations of image pixels, which is a big deal. All right. So mathematically, what this means? It means, okay, well, I want to digitally acquire the signal U, and A is a linear, is a matrix. What I know is not U directly, but I know A times U, and during the sensing process, I might actually introduce some errors because of my device. So what I know is B. Okay. So I design A. I know B, and I don't know U or W, and W is usually some kind of random noise. All right. Okay. And by the way, you see these kind of things because I forgot another dollar sign. It should be double dollar signs and W and double dollar signs. All right. Okay. Now, so the question is, well, what do I mean by this highly compressible mathematically? We know images as like this image. If you look at this, this edge is just the same, right? So images are usually very simple. So images are compressible, but what do I mean by it's compressible? Mathematically, you can write down an image as in this way. You can think it as a vector. Well, by image, usually people see it as a matrix, but you can stretch it into one big vector. So U is a vector, and D is something called a dictionary, and X is the coefficients of the dictionary. So D times X is just the linear combinations of the columns in D multiplied by the numbers in X. All right. And by the way, I wrote it a long time ago, so I didn't follow the exact notation. So this should be bold. This should be bold, but but I wrote it a long time ago. So, all right. So what are these dictionaries can be? It's a still open question. Lots of people are doing research on images, on different kind of images, and develop better dictionaries. It turns out this dictionary really captures a lot of important structures in an image. Right? So in the early days, the dictionary D can be discrete cosine transform. Right? A D corresponding to discrete cosine transform. We actually use it pretty much every day. That's the online technique in the JPEG. Online technique in JPEG. All right. So, and then later around the year around 1997, a bunch of people come up with something called wavelets. A large group of people. About 15 years ago, this is a very hot topic. About 5 years ago, it's still hot. And then people extend wavelets to something called framelets, and so on. So these set of dictionaries, as I will mention later, these set of dictionaries have very nice mathematical properties. So what's inside D are designed by people. So what inside D, for example, can be a bunch of cosines and a bunch of sines. All right. And what's inside of this wavelets can be a hard little hard wavelet and then stretched and translated. But basically, all of these dictionaries are designed by people. And they're analytic. They have very nice properties. You're going to sit down still for a couple of days, and you can derive a bunch of properties. And you can brag about these dictionaries. And these dictionaries are easy to compute. Let's say this D has a size n by n, the n rows, n columns. But usually multiplying an n by n matrix to a vector, it takes n squared time. But instead of taking n squared times, doing these transform or doing these dictionaries, it just need n log n time. So they are fast to compute. But there's a problem with these dictionaries, because these dictionaries are developed by human. They don't actually characterize everything. They don't adapt to the specific set of images you want to acquire. That's why people also come up with a bunch of learned dictionaries. So it's a set of learned image patches. I'm going to give you examples later. So these patches, these learned dictionaries, in other words, you can come up with a D that is out of an algorithm. And if you look at just the numbers one by one, they don't have any structure. Right? So they are purely learned from the data. Right? Okay. But anyway, you're going to have a dictionary that's gonna express U, and you're gonna only use a small number of non-zero coefficients in X. X will be a sparse vector. All right. Okay. Now, how do we recover the image? Okay, this is dictionary. There's a different approach. A different approach is it's an alternative to the dictionary approach. Instead of using a dictionary, you can try to find a transform such that applying this transform on the image, you get a sparse vector. Okay, there are also examples of such a transform. Now, we have two ways to make this image sparse. Now we know A and we know B. How do we know? And we develop either D or psi matrix. All right. How do we recover these? These are the standard models. These models mean the following. Okay, I'm going to minimize the summation of the two items. The first item is L1 norm of psi times U. I know psi times U is supposed to be sparse, right? Then it turns out minimizing L1 norm will often give you sparse solutions. And you're going to learn this lecture and tomorrow. All right. So minimizing this term usually going to give you something sparse, inside this L1 norm. But that does not fit this model. This is the important data. So we also have to fit this model, which means I'm going to come up with a U that matches my observations. Okay, so this is called a regularizer. Try to enforce a structure in the solution U, and this is called data fidelity, or called the loss function. All right, what you lose in terms of this model. Okay, so you don't see W. That's right, because W is unknown noise. W is supposed to be close to AU minus B. All right, I use 2 norm. There are other people using different kind of functions, but 2 norm is kind of nice, and lots of people start with 2 norm. Basically, you use 2 norm squared if you have Gaussian noise. If this noise is Poisson or other, have other statistical properties, you will use different functions here. Okay, all right. So these are the models. The applications are there are lots of applications, and it's just that you can't even finish talking about them in amounts. And compressive imaging. Now, lots of people ask me, when will I see a camera that does this? When will I see a camera that no longer scan the image pixel by pixel, but do this kind of fancy things? Well, you probably won't. You probably won't see it any sooner, because we're in some sense we're very lucky, because the visible light is basically a small band of the whole spectrum. Then the whole band is like this wide, and this part is visible light, as you can see. And we are very lucky in the sense that silicon are very sensitive to these bands. All right. So only when we have to visualize something in very low light, or when we have to see something in light, at night, and then you will have trouble, using silicon. But in general, visible lights are very easy to sense. So this won't be used on visible lights, but on other bands like an infrared lights have very low energy. You're going to use this, all right? For example, hyperspectral images. Hyperspectral means that it's not just a visible one, but actually very wide, like thousands of bands. You're going to use this, and also in other medical imaging fields, medical resonance imaging and computer tomography. These are indirect imaging methods. They picture your body without opening your body. Okay, and they actually already been doing this. So A in the MRI case is some kind of Fourier transform. In the CT case, this matrix A corresponds to something called a Rodon transform. And also, you may also have problems, having a low resolution image. You want to create a high resolution image out of it, or you have a low resolution video. Right? And then you want to somehow combine the neighbor frames to create high resolution images, and those will also actually correspond to some kind of different operators A. All right. So there's a whole long list of applications that basically use this model, and lots of people are doing this research, and we're actually benefiting from that. Okay. So this is pretty much the most basic sparse optimization model and applications, and lots of people are working on that. Now here are some illustrations. You can click on this, and you're going to get a bunch of nice illustrations. And I also already showed this picture. It basically compresses the image from 1.2 megabytes to only 40 kilobytes using a DCT transform. At least on my laptop, I don't see a difference. This is 30 times compression ratio. Okay. Okay, there are a bunch of other things. All right. So, and after that model, I would spend maybe a couple of minutes on mentioning this model, and this is also a nice model. It's an extension to the dictionary model. So in the dictionary model, you're going to model a vector. You're going to model a vector as the linear combinations of dictionary atoms, and you impose that the linear combinations is sparse. You can only use a few atoms from the dictionary. All right. So the only thing you put on the table is the dictionary and sparsity. But here there are going to be other structures. These structures are let's me see what the words she used. So the synthesis model mentioned by in my post bears a simple assumption, blah blah blah. This is actually a rough description of the online image. That's right. Under some scenarios, it is possible to impose additional structures, requiring its support to have specific structure if it is known, and this further helps depict online signal. That's pretty good. Okay, so this is the additional structure. It's here. It's called group pattern, right? So a group pattern basically looks like coefficient. Look at this vector u, right? So okay, so u in her post is the dictionary coefficients. Is not the signal. D times u is the signal. All right, u is a sparse vector. That are the coefficients of the atoms in the dictionary. All right. So when you see this kind of thing, people want it to be sparse. So what is this? Now this is a special notation. It's u sub something group I. All right. So what this group I means that it pick out a few entries out of u. Right. It pick out a few entries out of u and put them in the 2 norm. Okay. In other words, it's a long vector. You pick out a certain entries and put them together, right? And what did I do? I probably pressed some button on my remote. All right. So you have a bunch of groups, and you can define these groups. Actually, there are people studying how to come up with these groups from a bunch of images. Okay. So for example, this green board. The groups can be like pixels here, here, here. They're all the same. Now you can group them together. If I can sparsely represent this one, I can sparsely represent this one using the same atoms from the dictionary. They're similar. Whereas you're probably going to group these whiteboards, blackboard patches together, and you can also group these together. All right. Well, and those are numbers. If you have a part of a dictionary that describes numbers, and you can put those numbers together. Now, this basically is an additional structure that you can impose in the optimization. And it turns out when you have both there, and you properly select this parameter lambda 1 and lambda 2, you're probably going to get better recovery. Okay. And as I said, there are a bunch of people that are doing this. And there are some examples of these groups. It can be non-local structures. Basically, patches at a certain distance going to be similar in an image. And also edges. So edge in an image is a special feature that's very powerful. Okay. But the edge is not just when you take a gradient of edge, it becomes okay, so think about this image. This is the image, and it's not sparse because all of these are non-zero. These are 0. Okay, these are 0. This is 65. It's not sparse, but it take a gradient. You get a delta function, which is sparse. All right. So edge in the 2D image is like this, and you take the gradient. They give you a sparse one. They give you a sparse vector. But it's not just sparse, because and edges are also connected. In other words, these kind of sparse things are also connected. They're next to each other. So that's an additional structure that you can impose, and most edges are connected. And there are also periodic patterns here. So the patterns on my shirts, they're periodic, right? So they go periodic. You can also impose those structures. All right, this is great. Low rank matrix completion. And I'll mention this and the Netflix, and then I'll do the mathematics. All right. So this low rank matrix completion is very interesting, and it's very new. It's about like 3 or 4 years, and lots of people are working on that. So what is the background? The mathematical background is you have a matrix that is low rank, or maybe approximately low rank, and you only know a small number of entries of this matrix M. The goal is to recover the entire matrix. Now it's possible because it's low rank. All right, so a low rank matrix M a low rank matrix M like this, all right, can be written down as a tall and same matrix X and the short and fat matrix Y. All right, so if you count number of elements in this one, let's say it's M rows, R columns, and R rows, N columns. So the number of entries here is M plus N times R, right? And here it is M times N. All right. If R is small, this number is much smaller than that, which means there's lots of repetition in this matrix. Right? If you let's say you randomly sample some entries in this in this matrix, there are actually theory telling you that under some conditions, on X and Y, this entire image can be recovered. This is called matrix completion. Okay. The bunch of formulation down here, and this is one model. Actually, there are 3 different models to do this. All right, so let's look at an application of this. The application is the so-called Netflix problem. All right, so Netflix is an online movie rental company in the United States. So what basically do, I probably can even log in this Netflix. Let me see. All right, so actually I have an account. I can watch the movie online or rent movies online. I pay about $12 per month, and it's probably from China, so it's something get blocked. But anyway, so I can borrow a movie from that service. All right. The reason I keep account on this website is because it really recommends me good movies to watch. Right? So a guy like me, I'm busy. I don't usually watch TV every night. But when I want to watch a movie, I have trouble knowing what I should watch. All right. And this kind of movie website, they don't have the latest movies. To watch latest movies, you have to go to theaters. Right? And you get lots of comments, people talking about latest movies. So about latest movies, you know what you should watch. All right. But about older movies, the movies that's like 3 years old and all the way through like 8 years old. What are the movies you should watch? You don't know. So this company soon find out this problem, and they want to recommend users movies that they might like. If they do this well, they're going to keep customers like me, all right? Because again, if you ask me to sit there and write and tell you the movies I would like watching, I'm probably going to come up with maybe 20 movies or 25 movies. Then after that, I have no idea what I want to watch, all right? Okay. So basically, they need to learn about you, learn about your taste, and this is also called a recommender systems, all right? Now, what's the chances? The chances is it has tens of millions of users and tens of thousands of movies. In other words, they have lots of users to learn from. They have lots of movies to learn from. All right. So the data is some users will rate their movies, rate the movies they watched, and the ratings is something like 0 to 5 stars. Right? They send you an email, and you directly click inside the email, so they receive the data. All right. So what is the structure? The structure is M. M is like this. So M is like a matrix in which the entries are just the 0, 1 through 5. 1 means you don't like it, you hate it. 5 means you really like it. You probably want to watch it later, watch it again. All right. So the structure of M is nearly low rank. All right. This is a strong, very very strong argument. Why M is low rank? All right. That's really because there are only a small number of kinds of movies, movie watchers, and small number of kinds of movies. All right. For example, you like watching kung fu movies. You like watching 3 of them. You probably like to watch the rest of the kung fu movies as well, right? So they can lure you. There's only people argue there's about like 17 to 20 kinds of. They're going to be like 17 to 20 numbers that will describe all kinds of movies and all kinds of people regarding watching movies. All right. So what is that 17? 17 is this R. So in other words, this matrix has tens of millions of rows, tens of thousands of columns, but at the end of the day, this R is 17. It's something like 17. It may be not 17, but maybe 21, but it's like that. Right? So it means that if everybody watches every movie, you're going to be lots of redundancy in this rating. There's a pattern there. Therefore, you don't need to have everybody watching every movie in order to give you a complete rating. Okay. So the goal is given existing ratings, predict the missing ratings, and thus recommend users the movies they might like. It turns out they run this business really well. They had a $1 million prize a few years back. One of the teams won it, and that team actually used a set of technologies, set of tools that includes this way. All right. Okay. So there are a bunch of references here. The paper, the website with a special algorithm for this problem, and other people's lecture notes. All right. Now it turned out it's not just low rank. It's also some kind of sparsity here. There might be other patterns. I'll tell you a reason. All right. So it turns out when people rate movies or rate books, it kind of depends on what time they watch the movie. All right. If you watch a relaxing movie, if you watch a movie on Friday night, and your homework won't be due until 5 days later, and you probably are going to rate everything nice, at least 3 stars. But if you watch a movie just before the homework deadline, you probably won't rate it very high. Therefore, there's a pattern. It turns out this pattern can be also learned. The pattern will be learned out of something like this. Right? Okay. Now, not only patterns, people sometimes rate things randomly. Say you were working on your homework and you receive an email from Netflix asking you to rate a movie you watched last night. You don't want to rate it. You can delete email, or sometimes you just give a random rating. Well, there are people doing this kind of things, but random ratings usually are small. I mean, these random patterns can be detected. They are also in this kind of matrix. So therefore, the actual rating will be something like a low rank plus a bunch of other matrices that has structures. All right. So you will have to recover not just X and Y. You will have to recover S in order to correctly reconstruct this low rank matrix M. Okay. And there are more like sparse graphical models. This topic is really hot. Especially in the analysis of, say, Facebook data or Renren data. So they want to learn they basically want to learn the network of people and how these people form networks. Right. And there are also a principal component analysis. This is low rank, this is sparse. Also, there's also wireless sensor networks. The spectrum and the activities inside a wireless sensor networks will be sparse, so you will come up with models like this. All right. And I encourage you to read and put more applications down here. And notice that you don't have to read a lot. You don't really have to read a whole paper like word by word, but you just need to know, just need to provide people the rough background. What is this application about, and what is sparse and what is the basic model, and then some references. Right. I hope this post will gonna grow to something like 30 or maybe 50 entries. All right. Okay. So this is probably the only time, and I'm gonna mention these. And for the rest of this lecture, I'll probably gonna only touch some of these, but not gonna mention these applications. So I'm gonna switch to the main lecture. All right. The basic sparse optimization models. And at this moment, I need 2 volunteers who have registered for this course to take notes. And the earlier you thank you. All right. We'll have one. We need another volunteer who want to work with him. So I can tell you. So the earlier you raise your hand, the better, because the early lectures are simple. Lots of words, right? Very very little mathematics. Like next week you're gonna see a slide full of mathematics, and then you will have to type more, spend more time typing. So you want to do? Who else want to scrap this lecture? No? Oh, I do have the roster, so I can randomly pick one. Okay, well. So what are your concerns? What are your concerns? You think it's too much or too difficult to do or something? Maybe 2 days? 2 days? I mean, it's basically another 1 or 2 hours after the lecture. So I'm going to send you the LaTeX files of this lecture, and maybe just create a few more slides, or like add some words to this. Huh? Okay. So this gentleman and that gentleman. All right. Okay. Okay. So what's the purpose of this lecture? We're gonna see the basic L1, L2.1, and nuclear norm models, and basically argue why they will give you sparse solutions. And we're already seeing some of the applications. We're gonna reformulate them. We're gonna start solving them. All right. We're gonna reformulate them into standard conic programs. And once you go through these lectures, and this afternoon you're gonna be able to go to your MATLAB and solve some of these problems, at least the small ones. Okay, and then I'll tell you what are the solvers available to solve these problems. Okay, so basically at the end of the day you're able to solve small sparse optimization problems. Okay, so we've seen lots of applications from Piazza.com. Okay, something strange, because I have words here. It disappears. Okay, so let me recompile them. Okay, so I'm gonna open it with Acrobat Reader. All right. So these words reappear. So this is the most basic model. All right. In this basic model, we minimize L1 norm subject to constraints AX equals B. By the way, this is a compact way of writing down a optimization problem. All right. So whatever before the column is the objective function, and everything behind the column is the constraints. Right? So here I have linear constraints. Now most of the time you see these linear constraints, your teachers told you there's a unique solution. Right? But this is not the case here. So this one will have infinite number of solutions in general, and we are looking for a solution that has minimal L1 norm. Okay. Right? So it finds the least L1 norm point on the affine plane, AX equals B. Right? It tends to return a sparse point, and sometimes the sparsest point. Here's the reason. So I have a graph here. So every point on this surface, on the surface of this diamond, have the same L1 norm. Okay? They are equally good. So now I'm going to draw a plane that corresponding to all the points satisfying AX equals B. So this is plane, this dark region, this gray region, it has all the points satisfying AX equals B, and of course it's only one part of it. It extends infinitely. Minimizing L1 norm means that finding the least L1 point. What you can do is you can start with a very small diamond and grow this diamond. Growing this diamond means that you are getting larger L1 norm. You grow it to the point where it just touches this plane. So you grow this diamond, it touches plane, and it touches plane at, in this case, at x naught. X is superscript O, actually. That's something I call original point. Okay, at the red dot. Now you can see. Now let me get rid of the plane. You can see that the diamond shape is kind of very special. So these corners are very, very sharp. All right. So they come out to reach points first, reach anything first. If these points do not touch anything, usually these lines are going to touch something. All right, because they also striking out. But these flat planes are the last points to touch anything because they're flat. They do not come out. All right. So that's the naive reason why minimizing L1 tend to give you a sparse solution like that. It's not guaranteed, but often give you a sparse solution like that. All right. And there's another issue you can immediately imagine. If I move this plane a little bit, if I turn this plane a little bit, this entire plane can actually touch the entire surface. It's possible. All right, but only you have to turn it really well to a certain angle in order to touch this thing, which means L1 minimization may not have unique solutions in general. Okay? So it's good that often it gives you sparse solution, but the bad thing is it may have non-unique solutions in general. So we have to deal with that later. Okay, now this is the ideal model. There's no, everything is exact, but as I said, B may have noise. This vector B may contain noise. So when B contains noise, you do not enforce AX equals B. You let AX not equal to B to accommodate the noise. All right? And there are 3 different kinds of models you can deal with, but all of these models allow the solution x star not equal to b. A times x star not equal to b, which means geometrically it means you let this plane move along its normal directions. This plane will not stay there. You let it move. All right. So for example, this constraint just tell you the movement in terms of 2 norm is less than or equal to plus or minus sigma. Okay? So in other words, this half is like a sigma. Okay? Alright. Now, there's something to say about these 3 models. So, the first model minimizes 2 norm of AX equals B subject to a constraint on L1 norm. Alright. So if you ignore this constraint, it'll basically give you something called the least square solutions, which we reviewed last lecture. Now it just tells you that we don't want a least square solution, but we want a solution that has L1 norm upper bounded by tau. Alright, so you bound the L1 norm. So let's jump here to the third model, 2C. Now 2C says you want to find the minimal L1 solution, but you allow AX equals B be violated up to an amount sigma. Alright. Now the middle model is kind of similar to the 2, except that it has no constraints. What it does is, now you have 2 terms, you have an L2 term, you have L1 term. Let's somehow put them together and assign a weight vector and try to minimize their sum. Okay. So in some sense, these 3 models are equivalent. So I'm gonna in next lecture, in tomorrow, I'm going to tell you why they are equivalent. All right. So they are equivalent. Roughly speaking, I can find tau, mu, and sigma, so that the solution set of these three are exactly the same. Okay. But these models are also different. They have different applications. Now, the first model is usually referred to as bounded sparsity. You explicitly bound to the L1 norm, which means you want to enforce that X is sparse. The second model is called LASU, least angle regression or something. This is the very well-known statistical model. All right. And what it does is you make some observations of patients. Let's say B means some patients have this certain disease or not. B are, like, for example, 0, 1. A is a bunch of lab test results. So every patient will receive some tests, like a blood test and other tests. All right. Now, those numbers are encoded in A. You want to then determine whether a patient has a certain disease out of those test results. Assume that only a few test results will determine the disease. Then what you want to do is find out those few test results. That's called sparse. That's called a feature selection. Select a bunch of features that will express the observation B. If you say I want a sparse set of features, I'm going to put L1 there. All right. So statisticians often talk about this model, and they also talk about how to pick mu. All right. Okay. And this model is called a basis pursuit denoising. You call it a basis pursuit if sigma is 0, which means AX has to equal B. All right. And if B has noise, you let it be relaxed. All right. Okay. Now, okay, come back to these points later, because I also want to talk about how to select tau, mu, and sigma. And then once you start doing that, you're going to find trouble selecting these numbers. All right, but let me talk about other models first. Now we have seen this model. The signal U itself is not sparse, but can be sparsely represented by a dictionary like this. This looks like a DCT dictionary. If you do DCT MTX in MATLAB, you create a matrix corresponding to discrete cosine transform, and you picture it. You picture it. You treat it as an image and look at the image. It looks like just this. All right. So this is a DCT dictionary, and I'm going to only use 3 columns out of these. So this column vector has 3 non-zeros, corresponding to the second column, the 6th column, and some other column. All right. Okay. And the question here, this model is super simple, right? You just, instead of minimizing the signals L1 norm, you minimize the coefficients L1 norm. Nothing very special. But what's interesting is which dictionary do you use? So picking the right dictionary, and even determining the dictionary size is a research. All right. Okay. Now move forward. Now, of course, for the instead of making this using this dictionary model, you can use another model called by the way, this is called L1 synthesis. You synthesize. Synthesize means it creates. All right. Synthesize means you use something to create a signal. It's called L1 synthesis. This is if the L1 synthesis model, if this model, this psi is an orthogonal matrix. Orthogonal matrix means that, or Hermitian matrix, or unitary matrix. It means that psi transpose or conjugate transpose equals identity. All right. So actually, this one equals the inverse of psi. All right. So if you have this property, you can translate this model into a different way. So you can just do a variable change. You let x be psi times s, and then you can move psi to the other side, which is psi transpose. And then instead of using a synthesized model, you can do something like this. X is your original signal. Instead of minimizing s, you're going to minimize psi transpose x. All right? Okay. And there's a name for this model. It's called the L1 analysis model. You're going to look at the signal, analyze it. And there are a bunch of standard operators that analyze these models, and I'll tell you that I won't talk too much about this model, but this model is much more difficult to analyze than this model. This model will be easy to analyze because L1 is separable. It's summation of absolute values. But this model is more difficult to analyze because this term is no longer separable. Alright? Okay. Here's an example. And after this example, I'll give you a break. This is a famous image called the cameraman. Very famous. And then I do 3 different transforms. I do a DCT transform, do a hard transform, and take the local variation, take the gradient of this image. Alright, this is me taking the gradient of this image. And then these are the coefficients, the pictures corresponding to the coefficients. So DCT coefficients, everything is clustered to this corner, and then when you get away from this corner, it decays. Alright? So if you take these points out and sort them by magnitude, and this is what it looks like. This is log scale. This number of coefficients. It decreases. It doesn't decrease very fast, but it decreases. Alright? And also it tells you there's a small number of coefficients near this end that capture most of the energy. Right? And it turns out the largest coefficient will carry most of the information in the image. In other words, if you just keep these coefficients and zero out the rest of them, and do an inverse DCT transform, you're going to basically see the same image. Alright? So now, but this dictionary is not as efficient as this dictionary. This is hard wavelets. Hard wavelets, when you do this wavelets, you're going to see a tree structure. Alright? So this is low resolution, very low resolution image, very small, and then you're going to see basically some kind of changes, some kind of high resolution additions you're going to add to this image and give you your original image in some sense. And hard wavelets, if you come close, hard wavelet decays very fast. The largest hard wavelet is around 1000 and it decays very fast to 0. So in other words, if you keep just say 10% of the coefficients, you're going to almost recover the same image. Right? The same is true for local variation, except the local variation taking the gradient is not a dictionary. Now, I give you all the variation, you cannot recover the same image. All right? So this is not a dictionary. So this is some kind of analysis model, but it has the same features. Once you take the gradient, you sort the gradient by magnitude. Everything is large except everything is small except maybe the first 10%. That's why minimizing total variation will be an effective means to create these images. All right. So I'm gonna stop here. I'm gonna start with these questions. At the beginning of next lecture. Okay. And we should be able to finish around 11:30. Okay. All right. So let's have a 10-minute break.